Hey everyone, and welcome back to Tetris Coding. This is stream number 8 where we code Tetris in Odin with Raylib. And what we are going to do today is the super rotation system. We didn't get around to it on stream 7. We spent some time cleaning up some of the playfield code and doing some wall collisions so that pieces can't move left or right through blocks. And let me just show you real quick where we are. So we could place some test blocks down. We could move this tetramino that's active, and you'll notice it cannot move past the block. And also what we did on a prior stream to that is interesting, is that we could see the ghost of where the tetramino would fall, or if we press a button, that's where it will hard drop at. And what I wanted to work on today is the super rotation system. And I think it's really cool. I think it's one of the things that once you do it, it really starts to make it feel like kind of a modern Tetris that feel. And let me just go over briefly what it kind of is and how we're going to go about implementing it. So what it basically is say that we have okay, well, let's just look at it there. So let's say that we have some blocks that are in the playfield right now. So let's say this one is in the playfield, right? And then we have more blocks. So we have this thing, so that's also in the playfield. And then what we have is we have our active tetramino. And right now, let me extend this a little bit. And right now, this is our active tetramino, this eyepiece. And the question is like, so if it's here, and I'm not going to explain this accurately, I'm just going to explain this in a way to help illustrate it. So let's say that we want to be able to rotate this. So if that's right here, then it will go from here to be like somewhere in this position. And that's cool. And that was like a situation where like it's kind of embedded in something, but you rotate around it. But let's say that we have something that's a bit more like this, where maybe you have your eyepiece and it's kind of in partially, like let's say it's extruding one block here, right? And it's kind of in this wall shape, right? And let's say you rotate it. And let's say when you do rotate it, if the rotation point is there, you end up with a situation where your eyepiece, it's like this. And that can't happen. And one solution to that would just be say, well, we can't rotate like that because that would put you in an invalid rotation state. It can't be within these two pillars. But some Tetris games have different types of rotation systems that you could do some like finagling and finessing. So like let's say it does get embedded in here on the rotation. It'll have some sort of system that says, okay, that is embedded. Let's try moving it to a different location where it wouldn't be embedded. And let's say it determines that, okay, I can move it here. And it'll kind of like, feel good, like it rotated, it was embedded, and it seems like it kind of pops out of a certain area. And that kind of became, as far as I know, part of a lot of Tetris games' way that they feel, and some things that people will kind of know how a certain rotation system works for a given Tetris game so that they could use it to their advantage and have that knowledge when they're playing. And we kind of want to implement something like this. And then the other thing is like, let's say we do have this pillar, right? And the eyepiece gets like way down here, right? So when we do try to rotate it, it would end up like this. And because this is too far down in this gutter here, that would be a situation where, we just won't allow the rotation because it's too far down, and we don't want to make it so it completely pops up here to some type of valid position. So there are still cases where it will sort of get stuck and not be allowed to rotate. But then there's other situations where if it is like, say, near an edge of something and it could reasonably pop out and not feel like you're cheating against the game, then it'll allow to do that. And the one that we're going to implement is called the super rotation system. I'm pretty sure that this is the system that was used in Puyo Puyo Tetris, and probably some other ones. I'm honestly not a huge Tetris head, but I do know from what it seems like when I hear people talking about it, is that this is a very common one used today for a lot of Tetris games. And how it's pretty much implemented, well, let me just pull up the wiki page because we're going to reference this super rotation system. All right, so how it essentially works. So remember how I defined the rotations as like these enums? So let me go to the code. So like right here is the Z piece. And here are the different, so for the 0, the right, the left, and the 2 rotation, here are the shapes that they would be in Tetramino space. And that's really all I'm doing. So if I have my Z here, and if I rotate it, all it's really doing is swapping between one of those enum rotation positions. It's not actually doing like any type of translation or transform or anything like that. Literally just stepping through it. So how the super rotation system works is that you could perform these wall kicks, which is sort of what I described when a piece could kind of pop out. And I think maybe there's ones kind of called like ground kicks maybe, or floor kicks or something like that. But in any case, so let's say we have our Z piece. So I'm just going to pick that one as an example. What we're going to do is say you go from the 0 position to the right position, right? What we're going to do is just see, is that still valid? Does that collide with anything? If not, we don't have to do anything. We just do a basic rotation and we put it into place. And what this test means is an offset from where you would be when you rotated. So 0, 0 means like we're not going to move you at all. We're just going to test you right where you are and see if that is valid. So in the event that that is not the case and you collide with a wall. So let's say we have our Z piece right here and it just rotated, and when we rotated it, we have all these blocks over here that now this thing is intersecting, right? So now we need to move it somewhere else to test. And the first thing we're going to try is -1, 0. So what we're actually going to do behind the scenes is shift it over 1 so it looks more like this. So like before, in this situation, this is like a single block. Sorry for not doing a great job of drawing these. Okay, so a single block was in the wall, it collided, and now what we're going to do is shift it over 1 in the X direction. And we're going to test that. However, it's still going to collide, and that is not good. So then what we do is we try -1 + 1. So let's do that. So -1 plus 1, that would move it out, and I think down or up. I'll have to check whether or not, yeah, I think this is referring to moving it up in the y direction, but we'll check. So what this will do is it'll move it out. So there we go. So it moved it out and then it moved it up, right? And now you'll notice, okay, it's not colliding with the wall anymore. Let me just put -1 plus 1. It's not colliding with the wall anymore. So we are Gucci, and this can be a valid place that we place this Z shape. And we will test all of these to see if any of these will allow us to place a valid piece in. If none of them do, then we just cannot rotate it. The piece is sort of stuck in limbo, and we just have to deal with that for the time being. So one thing I want to clear up in my explanation is that what rotation you do determines the sequence of tests you did. And in this one, I was just like kind of making some stuff up, and I said, oh, well, you rotate it like that, and let's test it. But actually, the sequence steps that I took was actually if you go from the 0 to the right position. That would be the sequence of things you do. So I just wanted to clear that up because I was more just showing like an example. But yes, so what you go from like your old rotation to your new rotation is important for determining which sequence of tests you do. So yeah, positive y upwards. So the y goes in the up direction. So when we do this, we may have to, well, we will have to switch it around for the way we're currently doing positionings because our y's go downwards. Don't know if that is a good idea, but that is what we are doing because that is what Raylib uses, and not for any other particular benefit. And one other important thing to note is that the J, the L, the S, the T, and the Z all have this table, and then the I has this table. So it uses a separate set of data to do that. And you'll notice the O does not have a table, and that's because the O's just really don't rotate. We do have something in here to kind of have all their different rotation states, but they're all the same. There is no actual rotation that's happening, so they don't need to get tested. Okay, so let's see what games actually use it. So it looks like the Tetris the Grandmaster 3 and Tetris the Grandmaster Ace. And it looks like they use different data. So I was reading this and it says how guideline SRS super rotation system really works. And how this one works is that instead of like looking at what was the old rotation to the new rotation, and then getting the series of tests to do, what this one does is it gives you offsets for all the different rotations that you could be in, so say 0 and R. And what you do is you actually take the difference between those two to get the actual kind of like offset you'll use for the wall kick. I also just realized that a piece of a tetramino is called a mino. Okay, so I think I'm still gonna go with the original one up here that we were reading instead of this one under the section how guideline SRS really works, but maybe we will change that at some point if for whatever reason someone tells me, or if I get more time to look into it, that like this is actually like more accurate to other games, or if people have a preference. start getting into the code. So I think the first thing I want to do is get this table into code, and then just like, yeah, get the table into code, or probably like maybe at least like this first row right here. Get that into code. And then what we'll do is like when we rotate it, we will save for that frame what the old rotation was, and then use the new rotation that we have, see if there was a rotation, and then if there was a rotation, we will do the SRS. So let's do that. Let's go to the game, minus, minus, minus. Okay. So this is what does the rotation. And I think what we will do is just capture the old rotation. Old active tetramino rotation. And that will be the PST active tetramino dot rotation. Cool. And then what we will do, maybe let's also do the, yeah, let's just keep it like that. And then what I'll do is new. So if Q, what we will do is here we will set this to the new active tetramino rotation. And then for this, we will do the new active tetramino rotation. And then what we'll say is did want to rotate. And then that would be the old active tetramino is not equal to the new active tetramino, meaning it changed. So if did want to rotate, then what we will do is the super rotation system, and then I think this will take in, yep, the play field. And yeah, I'll just pass a pointer to it. And then what we'll want to do, so we pass the playfield state, and then the old active tetramino rotation, and then the new active tetramino rotation, and then the active tetramino itself. Okay. So yeah, the playfield state, the active tetramino, the old active tetramino rotation, and the new active tetramino rotation. Let's see if I'm forgetting anything, because it needs the old, it needs the new, and then it needs, it'll get this from the active tetramino, and then I think it will handle, it'll probably just like adjust in here whatever the new value needs to be. So I think that's probably what we want to call it. So let's make that super rotation system. And it takes in, let me move my Wacom tablet over here. Okay. So it takes in the playfield state, and that'll be a pointer to playfield width and playfield height. And it will also, why is this complaining? expected a type O of cell state. Okay, so it takes in the playfield state, and then it takes in the active tetramino, and that's a pointer to a tetramino. Dang it. Okay. And then we want to take in the old rotation. Or I guess really all we would have to take in is maybe the, because I guess we don't need to capture the old rotation, we just need to capture the rotation that you want to go to. So let's do that. New rotation, and that would be a rotation. And then down here, instead of doing the old, let's just, yeah, well, we could just like leave it like this and then just not have to pass in the old for now. Okay. So what we'll do in here is have some of this data, which is the rotation transition. Which would be a rotation. And that would be a rotation transition. Okay, and then a series of tests. And the test offset, which would be a 2int, right? I think so. So what we want to have, what would we call this? Wall kick data. Okay, wall kick data. And it is a questionable amount of rotation transitions, and then actually rotation wall kick data. Test offset. Wall kick data. Wall kick. Yeah, that's fine. Okay. And then in here, what we would have is the old equals 0. The new equals right. And then the test offset would be 0, 0. Cool. And JL TZ. JLSTZ. What I'm going to do is copy this and then paste it 1, 2, 3, 4, 5, 6, 7, 8, 8 times, I think. 1, 2, 3, 4, 5, 6, 7, 8, right? I'll just say this is 8. Okay, so we got 0, 0, negative. Oh, wait, and we need this for each test. So we actually need 8 of these here. And it would be, oh wait, no, 5, sorry. Num of wall kick test offsets. So 5. This would be the number of rotation equals 8. Okay. And this would actually be 5. And let's do that. And that. Okay, for 0 to right, use -1, 0, -1 plus 1, which would actually be -1, -1, and then 0, plus 2, and then -1 plus 2. All right, so we got that down, and then what we'll say is, so we're going to switch on the active tetramino type, and then for the case that it is J, L, S, T, or Z, we will use this guy for things. And then for the case that it is I, we will use the I related stuff. And then for the case in this, we need that. And then for the case for the O, we will do absolutely nothing. And then I think what we want to do is that if, so new, oh no, it's not new rotation. It's, we want to determine the new position that we want to be at. Okay. So what we want to do is for the wall kick data in, wall kick data for those guys, wall kick data dot old. So if the active, let's actually just put that up here. So rotation equals active tetramino dot rotation, and if the old equals, so if is matching, so if is the matching rotation transition, old rotation equals wall kick data dot old, and the new rotation equals wall kick data dot new. If is matching rotation transition, so that means we will use this test data. Do is what you said about that. So if it's matching wall kick data equals WKD. And then what we will do is try all these test data. So what we did right there at least what I think we did, barring any logical issues I may have made, is that we are just trying to find the matching rotation transition out of here. So 0 or right. And let's actually set all of these, oopsie daisies. Let's set all of these to be 0 so that we definitely don't get those out of there at any time. So what we're doing is we're trying to find the wall kick data to use based on these rotation transitions. And the idea is that we will get some test offsets out of that we want to loop over and test. So for test data in TD, TDO, I don't know. In the wall kick data test offsets, well, let's do that, test offsets. And this will just be offset. All right, and then what we will do is so for tetramino intersects, so what we'll do is we'll do the tetramino shape in playfield space. And we'll call this test tetramino, which will be equal to the active tetramino, and then change the test tetramino rotation to the new rotation, and then test tetramino. Oops, well, actually, let's just do that. And then this would be a tetramino p space. Or what did we say before T shape? P space. So this basically returns a tetramino shape, which is 4 minos actually, instead of blocks in tetramino. That's like 4. There's 4 minos in a tetramino. That's what tetramino means, I guess. All right. So then what we're going to do is once we have that test tetramino and we have the offset, what we're going to do is the test tetramino dot position. Actually, we should probably do this in every call here. What we're going to do is the test tetramino position plus equals the offset. The rotation gets set to new rotation. And let's actually, yes. And this takes in a tetramino, and then it returns a tetramino shape. And then what we want to do is say so what we want to do is for the mino p space, in T-shape p space. We want to see if that intersects equals intersects with block or wall. And what we will get if intersects with block or wall, the tetramino, so that would be the test tetramino. Oh, we could just pass in the whole tetramino here. We don't need to go over all the minos. Even better. Intersects. So if not intersects, I'm just thinking if we should do like a valid offset outside of here and set it, or if we should just not. I don't know. So if it intersected, or if it didn't intersect, so that would be is valid. Then I guess, or is valid position. Then I suppose what we would want to do, or is valid rotation, right? Then what we would want to do is the active tetramino position gets set to the test tetramino position, and the active tetramino position gets set to the test tetramino position. The active tetramino rotation gets set to the test tetramino rotation. And then I think we're good. So we'll like break out of there so we don't do anything else, right? I think so. And then I think we're basically at the point where we could test this out. So we just use the old rotation to check for what we're looking for. And then the new rotation we use in this test tetramino down here. And then we'll use a test tetramino position and rotation to set the changiness of all this. So let's build it. And immediately we get an error because we're always supposed to do rows and then columns. Okay, so I think let's try that with something, a J, a Z, I don't know. And what we want to do is if we go from 0 to right, so, well, let's see if it just works as it should now. Yes, it works. Let's even just verify that it is in fact going through the SRS. Oh, just right here. And that it gets a valid position. So let's do that. Okay, data and test offsets. This is all 0, 0, 0, which is what we expect. Try that again. And then all these test offsets. Okay, so this is actually the one that has the data because I'm guessing we moved from 0 to right. Let's see, is the active tetramino, the rotation 0, and the new rotation is right. Okay. And then what we do is we set the test tetramino equal to the active tetramino, so it's a z. The position is 1 over 2 down, that looks right, rotation is right. And we had set the new rotation and the offset, which was 0, 0. And then we just see if it was valid, which it was, and then we continue on our merry day. So let's get back to the 0 position here. And let's test what happens in this situation where when we rotate it, I believe it will collide this time. Maybe, we'll see. Okay. And we found it for this offset of -1, 0, which that was test 2. So we found the valid position. So the active tetramino was at 1, 7. The test tetramino is at 0, 7. Let's see if it gets bumped out appropriately. So yeah, it looked like it got bumped out, I guess. Let's even put all that there. Okay, well, might as well fill the rest out and see if it seems all peachy to us. All right, let me just copy all this in here so I can see it. Whew. Let's build that. And then let's see if we start getting some interesting things happening. So I would expect when I rotate that, so we're in right, and we're trying to go to 2. We don't get any valids. So let's just put a breakpoint there, and then try rotating. And see what happens. It does stress amino. The offset don't work. In the left. Over. And what is the offset this time? 0. Oh, it's still 0, 0, huh? Did it not find? Oh, all these are 0, 0. Well, that's weird, which means this one didn't get set. It did not find, so old rotation was right, new rotation was left, and we will have to go in here and see why that's doing that. This did not find a matching guy, so we need to figure out why it's not finding a matching guy. Let's try that again. Okay, so the wall kick test status is that we have 0 right, and our old rotation is right, and our new rotation is left. Wait a second. That can't happen. That can't happen. Old rotation is right, and new rotation is left. What? How in the heck does that even happen? because if we're going to right, then we can only go to 2. Right. Oh, wait. I guess can go right. Oh, my goodness. We totally messed up. I don't think that this... So, successive counterclockwise. I believe that anywhere we had left up here when we defined the shapes, this should have actually been 2, and then that should have been left. Oh my goodness. What a bug. So let's change that. Left, left, left. Let's do 2, 2. And then, or, yeah, 2. Let's do that. And then anytime we do this guy, that will be a left. And let's go back to any place we had the 2, 2. And change that to a 2. Oh my god. What a shock. That is a shocking bug. So let's build that again. And let's try rotating it. Okay. And now we actually get that kind of like finesse feel there, right? And then that rotated there, and then we'll try it again, and then it goes up. See that? Did you see that? Catch it? It's pretty cool. Look. And then, boom, it gets moved up. Then you're up here, floating around up here. Whoa. Is that right? So if I go there, and then I go down, if I go from 0, we have a bug in the way we're doing our ghost that we'll also need to figure out here. Well, let's mark that as something we need to figure out. Just take a picture of that so we have it for later. Okay. So I think what I'll do is continue to go through here and do the rest for the eyepieces now. Wall kick data. We'll actually define the wall kick data out here. And then find it within here. And then for this, yeah, we don't even need to do for O. We could just do nothing. And what we'll actually do is, and then what we're going to do for in here is just set it to wall kick data set equals that one. And then for in here, the wall kick data set is equal to that one. And then we will take this stuff and move it here. And then here, and then we'll just do for the wall kick data set. So yeah, really all we're doing now is that the, oh, actually, let's do this. Let's do that, and then do this. So essentially now for the j blah blah blah, we fill it like so, and then for the I we fill it like so. Although we're actually going to change out these values in a second here. And then for the O we do nothing and it's going to be 0. And then that's like fine if it's 0, and it will just like it'll be valid on the first one because the 0 can't really rotate. All right, so let's get all these guys. All right. So now all I'm gonna do is just go to my eye and see if we are getting things that look so let's verify that we are in fact going in here and getting this data set. So yes, we are. And then for the wall cake data set, matching one. And then what we're gonna do, test offsets in here, test offsets in here, and we do get one that is a -2, right? So yeah, if we go from right to 2, is that what we're doing? From 0 to right. It gets the 0 to right? Oh, sorry. Go right to 2. That is right. So it gets right to 2. Well, let's set this up and then see what happens there. We'll see if that is right. Maybe if that is right, that's an indicator that something is going according to plan. All right, is this the actual setup here? Let's see. So if we come in here, does that line up? So empty, 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 dun, dun, empty, empty, bum, bum, bum. And then we are rotating from 0 to the left. Well, definitely got put in the position that's there. All right, well, definitely got to put into the position that's there. So I'd say that that's fairly good. And then O, poor little O, didn't get any action in the limelight. And that's pretty cool. That's pretty cool. That it like moves around like that. That's kind of like what I meant when I was like, it's the first thing that starts to feel like really Tetris-y. Like where things like finagle around like that. That's cool. Yeah, it's starting to feel pretty good. All right, so that's pretty good. Let's just get rid of some of this cruft. Okay, so just as a recap of what we did. So really all we started to do was, instead of just like moving the rotation within the active tetramino, we just made a new active tetramino rotation. And then based on the key press, we're moving the new one that we're requesting. And then if it changed, we are calling the super rotation system function. And we started by like writing the function here, like the usage code, I suppose, where we thought about like what it would want to take, which is a playfield state, the active tetramino, and the new rotation we want to go to. And then after that, we actually wrote out the function. And how we are doing this is using these tables for these pieces and this table for the I piece. And depending on the piece that we have in, we construct a new wall kick data set. A different wall kick data set depending on the shape. So J, L, S, T, and Z, and then the I. And this is what we fill in here. And the O, we just don't change anything. We just leave the wall kick data set as like zeroed out because it won't matter anyway for the O. Then what we do, we go over the wall kick data set and we find the matching rotation transition based on the old rotation that we had and the new rotation that we want to go to. If it was matching, that is the wall kick data that we set. So we're looking like, so say we're moving from right to 0, we will extract this one that I have highlighted. When we have that extracted, we will then go over the test offsets in that data and make a test tetramino that we're going to test to see, is this a valid position that it could be in? And if it's not a valid position, we're just going to go check the next one. And if we don't get any valid positions, we just say we can't rotate this. If there is a valid position, meaning we rotated it, and then there is no intersecting walls or other blocks, then we just set the position to the test pause and the rotation to the test pause. And then we break out of there, and our piece is actually placed. So I'd say we could call this done. I don't know, maybe there's like some issues or errors in here that I didn't quite fully see, or maybe we'll want to take more of a look at the how guideline SRS really works, depending what I look into. Or if anyone out there is a Tetris pro and can comment on that, that would be very helpful. So let's just mark that as done for now, and then we'll come back to it later. And then the other thing I wanted to point out is that we seemed to have a bug in the ghost for the L's and the J's. Specifically, when the top one collides with a block. And what I mean by top is like one up here. Does that happen with these? It doesn't happen with those. It didn't happen with the S's or the T's, I don't think. It was only happening with the gels, the J's and the L's. So next time we're going to figure out what that's all about and fix that. And some other things I think we'll want to do. I think what we'll also do is get like some like row clearing logic happening. So if you like do something like this, where a row gets completely set here, that will clear, and then the wall will kind of fall downward. I think that's what we'll also do. What we're kind of doing is building out all of the kind of like logic that can be built out without necessarily needing to make the tetraminos fall yet and like have the falling action. Because I think we want to have most of that built out, so when we do start to implement the falling logic, and like locking pieces, soft locking and everything like that, then like a lot of things will just kind of fall into place because we've already implemented them. And that would be opposed to like, say, starting with the falling logic and then trying to create all these different mechanics that are going on. I think it'll just make it easier for testing, and I think it makes more sense. So yeah, thank you everyone for watching. And yeah, this was a cool video to do. I will see y'all next time.